Good afternoon. My name is Xiaochuan Tian. I'm now a postdoc at Boston College. Today, I would like to present to you our research about recent intriguing data of global warming before continental flood basalt volcanism. And we propose a model to explain how intrusions might be responsible for that. This work is done with my PhD advisor, Roger Buck, at Columbia University. Here's the take-home message in one sentence. Intrusion-induced crustal densification may be necessary for major continental flood basalt eruptions, and the intrusive CO2 release could cause global warming 100,000 years before the main phase volcanism. Let's first take a look at a recent global compilation of paleo temperature across Cretaceous-Paleogene boundary. Time goes from left to right. Vertical axis is mean global temperature relative to today. The data show a clear 2 degrees centigrade global warming 100,000 years before the KPG boundary. On the other hand, recent geochronologic data using argon-argon or uranium-lead methods reveal high-precision Deacon Traps eruption tempo, indicated by the brown and red curves. Though differ in detailed eruption rates, both agree that about 3/4 of total eruptive volume was in place after the KBG boundary. For another large in its province, uranium-lead geochronology of Columbia River basalt group indicates that 95% of the volcanism was erupted 300,000 years after the onset of global warming at about 17 million years ago. So, for the two most recent and best studied LIP climate pairs, both show eruption rates are out of sync with the global climate data, and volcanic CO2 outgassing cannot explain the warming that precedes major volcanism. Why warming happens a few 100,000 years before the main flood basalt volcanism? To address that, we need to investigate timing of volcanism relative to that of warming. Most simply, according to Archimedes' principle, lighter material floats whereas denser material sinks. The Earth is a little more involved. Here is a global average continental crustal density profile based on worldwide seismic experiments. For simplicity, we approximate it with a simple linear function. The lithostatic pressure at any depth can be calculated by gravitational acceleration g times the integration of crustal density with depth. And the density integration is equivalent to average overburden density times depth z. For a 20 km of upper crust, its overburden density is indicated by the green vertical line. Now, for a thought experiment, let's consider a glass of crust with the same density and pressure profile on the left. If we have a mid-crustal seal with typical magma density of 2,800 kg per meter cube, the mean overburden density is indicated by the green line. Because magma density is higher than average overburden density, even with an open conduit, magma can only rise to a depth still beneath the surface. However, many geophysical evidence indicate mid-crustal mafic intrusion beneath several LIPs, including the Deacon Traps and CRBG. For example, under the Deacon Traps, Panday 2008 show denser intruded crust as compared to the global average, and lithostatic pressure increases due to this crustal densification. With higher magma reservoir pressure due to the elevated lithostatic pressure from crustal densification, now the average overburden density is higher than that of the magma. With an open conduit, basaltic magma under higher pressure can now erupt. As shown above, the timing of major eruptions is mainly controlled by magma density relative to that of the average overburden density. Note that a few other mechanisms have been proposed for controlling the tempo of LIP eruptions. but they cannot explain the time lag between the warming and the major eruptions. Given the limited time, we won't discuss them now, and please refer to our paper for details. Here, we focus on how sill intrusions might change the crustal density structure, hence controlling the timing of major continental flood basalt volcanism. To do that, we build a simple 1D sill intrusion model that determines eruptibility of magma by calculating evolving density and thermomechanical conditions of the crust due to a series of sill intrusions. Each sill intrusion brings in heat and adds basaltic magma into the crust, which densifies the crust after solidification. Hence, the average overburden density increases and the magma eruptibility shifts from mainly intrusion to mainly eruptions. Our approach is similar to Annan et al. 2006, but we further consider depth of intrusions based on the crustal conditions. As shown here from the schematics, we assume a model-level magma reservoir sourced from the decompression melting of a mantle plume. The model-level reservoir then supplies melt for crustal sill intrusions, and we here calculate evolving sill intrusion depth at maximum breakout pressure, which is determined from magma overpressure minus the resistant pressure. Note that the resistant pressure is mainly a function of temperature. As shown here from the green shady area, at cooler, shallow depth, magma freezes quickly, and so it would be much harder to intrude a large sill near the surface. The magma overpressure is mainly affected by crustal density structure. Denser the crust, higher the magma overpressure. The model develops in 4 stages, assuming a magma intrusion flux with Gaussian shape. The model calculates sill intrusion depth accordingly. That allows us to calculate average overburden density and determine eruptibility by comparing that to the magma density. Here is the initial temperature and density structure. The blue and red dashed lines are magma solidus and liquidus. To the right is the global average crustal density structure that linearly increases from surface to manhole. Right now, the green mean overburden density is less than that of the magma density. The model favors intrusion. As sill intrusion flux increases, a series of sills intrude at shallower depths. CO2 exhausts from crystallizing magma shown as the bubbles. As the mafic intrusion solidified, they also densified the crust. Mean overburden density is still less than that of the magma. The model is in intrusion mode. As the flux peaks, the sill intrudes to the shallowest depth. Through this series of sill intrusion from stage 1 to 3, the crust becomes denser. Exhausted CO2 traverse the crust and add to the atmosphere, causing warming. At this stage, mean overburden density is still less than that of the magma density. The model predicts intrusion mode. The shallow thermal gradient is very high, and so the heat loss from the surface is fast. When the heat input from the intrusion cannot keep up with the heat loss to the surface as the intrusion flux decreases, the crust will cool and resistant pressure increases to prevent shallow sill intrusions. Finally, as the melt flux decreases, sills intrude into deeper depths. Now, mean overburden density is higher than that of the magma, and major eruptions start. We know that CO2 solubility in magma is pressure sensitive and highly incompatible, along with field evidence of high CO2 flux at actively intruded area like Yellowstone and East African Rift. It is reasonable to consider CO2 could exhaust from rising and crystallizing low viscosity basaltic magma, traversing the crust via faults and vents and add to the atmosphere. Geochemistry studies indicate 0.1 to 2 weight % of CO2 concentration within primitive mantle melt. For simplicity, we pick 1 weight percent and assume intrusive and extrusive outgassing efficiency of 55 and 70% following previous workers. This allows us to compute a magmatic CO2 outgassing flux. Now, for the timing of warming, it is a function of atmospheric CO2 concentration, and we input a calculated CO2 outgassing flux into the simple Lasker model for climatic response. Here is a video for decant traps. Panel A shows climate data and model results across KPG boundary. Panel B shows intrusion depth and magma input flux. Bottom panels are temperature, density, and pressures. As the model starts, magma flux increases with seal intrusion depth and decreases. Intrusions add heat to the crust and it gets warmer over time. The intruded places become denser. No eruption happens as mean overburden density is less than that of magma. Warming also reduces resistance pressure so that seal can keep intruding into shallower depth as flux increases. The intrusive CO2 release is added to the atmosphere, causing warming. As the flux decreases, seals intrude deeper. Because previously made intrusions have densified the crust, average overburden density now becomes higher than that of magma density, and eventually eruption mode starts. These results reproduce the observation that warming happens before major eruptions. Also adding here is the density profile on the decant traps for comparison. Note that the Columbia River basalt group and Miocene climate optimum case is very similar, and we won't have time to show here. I will end here with a take-home message, and thank you for your attention.